From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. The weather is so nice outside. I'm glad to see that you came to class anyway here. Well, Gaussian beams, what we were talking about last class, so let's go back to that. So we had started right at the end of the class. I'll repeat just the last couple, 3 minutes of class. We said that if we have a paraxial wave, we're saying that the wavefront normals are paraxial rays in that case. And we said we could have a complex amplitude here that would go as, say, A of R, e to the minus I, k, z. And we're saying that A of R is a slowly varying function of position. Okay. And then we went on to say that U of R here must satisfy the Helmholtz equation. And so we had that del squared U plus k squared U is equal to 0. And then the point that we're making here is that A of R is slowly varying. And so we can say that the second derivative of A with respect to Z can be neglected. Since A of R varies slowly with respect to Z. Okay, my pen is dying, so I'll switch colors here. Okay, and then just I think at the end of class, what we were doing then was to plug this into the Helmholtz equation here. And we had here that del squared sub t, we'll define that in a second, of A, minus I 2k partial of A with respect to Z is equal to 0, where this del squared sub t is second derivative with respect to x plus the second derivative with respect to y. So this was the expression then that we had here. And from this, we need to solve for A. And one simple solution here would be that A is some, say, A1 over Z, e to minus I k rho squared over 2z, whereas normally rho squared is x squared plus y squared. So this would be one possible solution, and we've seen this before. This is just a parabolic wavefront. So it's the paraxial approximation of a spherical wave. And so that's a solution. But what we want to do for the solution for Gaussian beams is the following. We have that we can simply take z, and so replace z with z minus squiggle, okay, where squiggle is a constant. So this is just a shifted version here. And so we could rewrite this if we want to. We could say, well, let q equals z minus squiggle. I'll write that down in a second here. But what we could say then is that a of r is a over q of z e to the minus ik rho squared over 2q of z, where q of z is equal to z minus squiggle. Okay, so no reason why we can't do that. You might question why we want to do that, but there's no reason why we can't do it. Okay. So we just have a parabolic wave now that's centered about the point z is equal to squiggle instead of the point that z is equal to 0. Now the next thing we want to do is we could say let squiggle is a constant. Well, let squiggle be complex. Okay, no reason why we can't do that. And what I really want to do here is to let squiggle be purely imaginary. And say that squiggle is equal to minus I z naught. Okay, z naught's again just some constant. And so now what we have for a here is that we could say, well, a of r is a1 over q of z e to the minus I k rho squared over 2q of z, where q of z is equal to z plus I z naught. Okay? And I'll draw a little box around that. So we simply have found a simple paraxial solution to the Helmholtz equation. And then we shifted our point of z from z is equal to 0 to z is equal to squiggle here. And then we said, well, let's, squiggle could be real, it could be complex. And we just said, well, let's make it purely imaginary. And we just gave it a value here of minus I z naught. So that still would satisfy the Helmholtz equation. And now what we're going to do is to just rewrite q. So q is some complex number. And it turns out here this z naught is going to come up a lot, and it's going to be what we call the Rayleigh range, but I'll write that down now. Okay, well, we could rewrite q. I mean, q is some complex number. Don't know what it is, but just some complex number here. And so I could write here, or we could write that 1 over q of z is 1 over r of z, some number. Anyway, this is going to be real. Minus I times something we'll call lambda over pi w squared of z. Okay. So right now I have no idea what r is and w is and so on. It's just that I'm rewriting this. It's a complex quantity, and so I could take 1 over that, and I'm going to get a complex quantity again, and I just put in some symbols here for those. And then we could solve for what r is and w is and so on. It will turn out in Gaussian beams that W of z, so it turns out that W of z and R of z will turn out to be measures of the beam width and the wavefront radius of curvature. I mean, there's no way we can see that right now, but it's going to turn out that's what it is. Okay? Well, what we can do then, with a lot of work, and I'm not going to do it here in class because there's other things I'd rather talk about than to go through all the algebra here. But it turns out that we can take this expression for 1 over q. We could plug that back into this expression here. And then we could go back to our basic expression for u right here. And we could play with the algebra a lot. And what we would come up with, and I guess the interested student will do this, what we can come up with after some work is that u of r would turn out to be some quantity a naught, where kind of right down here, the a naught would be equal to this thing we had a1 before divided by I z naught. So u of r, with a lot of work, turned out to be a naught w naught over w of z e to the minus rho squared over w squared of z e to the minus ikz. So that will just be a phase due to propagation along the z-axis. And then minus I k rho squared over 2r of z, so that's a parabolic phase. And then there's another thing that's going to be an I, not quite what I call squiggle, but I'm going to rename it squiggle anyway, of z here. And these quantities, instead of writing all this down, why don't I go to the handout I gave you. I'll just go to the first page of the handout that you have. So if you go through a lot of algebra, and if we can zoom in, we'll first zoom in on this. So this is a handout I gave you class or whenever. So this is just our expression for u. That's true if w of z here is w naught times 1 plus z over z naught squared, square root of this. R of z is z times the quantity 1 plus z naught over z squared. And this phase factor here is equal to arctangent of z over z naught. And w naught is lambda z naught over pi square root. So if we took the time to go through all the algebra, this is the expression we would get for the amplitude where these quantities are defined as down here. And as I said, the interested student who has plenty of time, maybe that qualifies or eliminates everyone here, I don't know. Interested student has plenty of time, can go through the algebra to show if this is true. Okay? I'm not going to do it in class because I have other things I want to do today. I'll drink my coffee here first. Okay. So someone recommended that I change coffee suppliers. First off, for the same price, you get more coffee, so that's good. And also, not bad coffee. See, some of you got coffee outside here. Are they still connected to the sewer pipe? That's what it was the last couple of weeks. It used to be very good coffee, and I don't know what happened. Okay, anyway, we have these equations here. And now what we want to do is to kind of look at these equations to learn a few things about Gaussian beams. And this is a little bit like a cookbook, maybe, I guess I would say. And so we'll go through the handout that I gave you here. So we could go through here and from this calculate the intensity, if you allow me to use that word, the intensity here. And maybe I'll put this off to the side because we'll come back to that. And we have here that I is a function of rho. So that's the distance. Remember, rho squared was x squared plus y squared. So that's the distance from the axis. N is a function of z. So as we propagate along, goes to some normalizing factor I naught here. W naught over WZ squared, e to the minus. Well, it's a Gaussian beam. If we go across, we fix z and look at the beam profile, it's a Gaussian beam, e to the minus 2 rho squared over w squared of z. And what we have here is a plot that is showing what happens as we move along the axis. And there's a location here which we define where z is equal to 0, where this is normalized to 1. And as we move away from z is equal to 0, the intensity is going to drop off. The beam is going to spread out. And kind of the interesting point that comes up many times here is, what if we go a distance, this quantity z naught, away? And if we go a distance z naught away, and we just go back to our expression right here, and plug in that z is equal to z naught, so we would have 1 plus 1, square root of that. So it's a square root of 2, or if we take the ratio of w squared over w naught squared, that would be equal to a half then. And so if we go a distance z naught away from this place, it's going to be called the beam waste here, the intensity drops by a factor of 2. Okay, so that's kind of an interesting thing that when we go to our summary sheet we'll remember, I guess. Okay. This is only on axis. We've set rho equal to 0, so this is on axis as the beam propagates along. There's a maximum intensity, distance z naught away, it becomes half of that. If we go to any z here, and we integrate over all space here, so that's down below. So we take the intensity, it's a function of rho and z, fix z, and integrate over rho, so 2 pi rho d rho, rho going from 0 to infinity. The power here turns out to be 1/2 I naught pi w naught squared. And so, I mean, this is independent of z, which I guess it better be. I mean, we have conservation of energy. As we look here in any plane, the total amount of energy is going to be fixed. It's just that the distribution across the plane is going to change. Okay. This W naught, W of z factor, I should say. So we have that expression on the first page, but I'll repeat it since it's on the next page of the handout here. Yeah, right. It's that's why I said you have to allow me to call it intensity. It's a book I stole it from, called it intensity. Brian Thompson at the University of Rochester says if you're over 40, you're allowed to call it intensity. So I can call it intensity, but you people have to call it, what do you have to call it? Irradiance, okay. Right. So there are a few advantages to getting old. Actually, that's the only advantage I've been able to think of so far, but anyway, there must be some other ones. Okay. So anyway, we just rewrote here that from the first page, Wz is W naught times 1 plus z over z naught squared, square root of that. And if we let, and so we're making a plot here of w of z as a function of z, and we get something that goes like this. And at z is equal to 0, that's where it's w naught. And as we go out here, it approaches a straight line here. And if we plug in here, let z become very large, then w of z is w naught over z naught times z. And so that's some quantity here we'll call theta naught times z here. And I guess also going to the first page here, I'll write down, I want to derive this equation here for beam divergence. And if we just go to the first page where we had w naught is lambda z naught over pi to the 1/2. And so that implies here that 1 over z naught is lambda over pi w naught squared. And so then we could say here that theta naught is lambda over pi w naught. Theta naught here just is w naught over z naught. So the beam divergence here is lambda over pi w naught. And if we go in both directions here, then that would be 2 over pi lambda. Or we could write, excuse me, we just write that still in just one direction here, but it's 2 over pi lambda over 2w naught. Now the reason we kind of wrote it this way, this is sort of like a lambda over the size here. Now the Gaussian beam, I mean, it doesn't just stop right here, it goes on forever, but we've picked a size here that we're going to call the beam waist here, and that would be w naught plus w naught or 2w naught. So that's sort of like a lambda over d. So if we kind of compare this to normal light here, normal beam, we have diffraction. If we have a beam of diameter d, a uniform beam of diameter d, the divergence we say goes as what? Lambda over d. And for the Gaussian beam here, so we have a lambda over something like d, and the beam divergence goes a little bit less than that. It goes 2 over pi times lambda over 2w naught. So it's similar to normal, what we think of for normal uniform beams. Okay. Before I go on, I was saying that the one advantage of being old is that you can say intensity. I found a second advantage recently when I went to Hawaii, and I went up to the Keck telescope, which is up 14,000 feet. That people, when you go up there, you're bound to, you can get dizzy and you get headaches and stuff. And the thing that happens is that higher altitudes, your brain begins to swell. But this is the second advantage I found to being old. When you get older, your brain actually shrinks, okay? And so going to high altitudes bothers older people less than it does younger people. And there was some young kid on here, 12 years old or something. Oh, he was dizzy and headaches. He was feeling terrible. Unfortunately, I felt nothing. I was so depressed that no headaches, wasn't dizzy. I don't know. Bad sign, I think. Anyway, beam divergence here. Depth of focus is the next item. Well, for the depth of focus, well, let me write down a couple of equations here, and then we'll see where we get to this depth of focus factor. We had, from the beginning, we had that w of z was w naught, 1 plus z over z naught squared, square root of. At z equals z naught, we have that w of z is square root of 2 w naught. Okay. Also from the equations on our first page here, we have that W naught is lambda Z naught over pi square root of. Okay. And so we have here that Z naught is pi W naught squared over lambda, which we could write as pi over 4, 2 W naught squared over lambda. In a second you'll see why I'm writing it that way. So this depth of focus here, as we define it anyway, which is this distance to Z naught here, which is where the beam changes from W naught to square root of 2 W naught. This distance to Z naught, which we're going to define as a depth of focus, goes as 2 pi W naught squared over lambda. Okay. So let's kind of compare that again to what you would get for normal uniform beam. So let's say we have a uniform beam. So what we want to find is what I'll call the classical depth of focus. And I don't think we defined that in class here. Do you know from the other classes what that is? No. Okay. Well, I'm not going to derive it here. Again, if I can talk you into taking 513, I promise we'll derive it there. But that turns out to be what we normally call plus or minus 2 lambda f number squared. And there are a couple ways to get to that. One way is that if we look at where the geometrical blur is equal to the airy disk diameter, we'll turn out that that's what the classical depth of focus is. And I think it also turns out to be where the defocus is equal to a quarter of a wavelength. So anyway, the classical depth of focus for your camera lens is plus or minus 2 lambda f number squared. And I guess if the wavelength is half a micron, this would be like plus or minus the f number squared in microns. Okay, so that's the classical depth of focus. The spot diameter, airy disk diameter, is 2.44 lambda f number. And so the depth of focus here we could write is 4 lambda spot diameter squared over 2.44 squared lambda squared. And so I don't have my calculator here, but that will turn out to be something like 2/3 spot diameter, airy disk diameter squared, divided by the wavelength. So that's the classical depth of focus. And what we got here, 2/3, 4 over 2.44 squared, which is something like 2/3 anyway. So this is the classical depth of focus for a uniform beam in terms of spot diameter. And what we got for the Gaussian beam was that the depth of focus here was equal to 2 pi times the diameter here at the beam waist squared over lambda. So in the way that we've defined depth of focus here, this is somewhat larger than what we have classically. Okay. The next guy here is kind of the most interesting one of the whole bunch. But you have to promise not to ask me to explain this one physically, because it's really strange here. But if we go back then and calculate what the phase is, well, we had the phase right here. I, kz, and then k rho squared over 2r, plus this other sort of like squiggle term. And so this phase here, we can write, it's just as I repeated here, kz. So that's, as we propagate along the z-axis, that makes sense. That would be the phase, just do the propagation along the z-axis. And then this is our parabolic approximation. So that's k, 2 pi over lambda times rho squared over 2r. And r is a function of position as we go along here. But then there's this other term here. And this other term turned out to be the arctangent of z over this z0 guy. So this is kind of a strange phase retardation that we get relative to a uniform plane wave. We just look along the axis so we could make rho equal to 0. You would expect the phase to go just as kz. But the phase actually goes as kz minus this other factor here, which, as I said, was the arctangent of z over z0. And so this other factor here goes from minus pi over 2 to plus pi over 2. And at the beam waist here, it's equal to 0. I don't know. That's kind of a strange, kind of an interesting guy here. And I cannot explain physically why that happens, but it's kind of an intriguing little factor here we have. Are you intrigued by it? Sort of, okay. Hard to explain. Okay, the next one we'll look at here, kind of go over a cookbook of things, is the radius of curvature of the Gaussian beam. So the radius of curvature here came back from this expression, r of z. It goes as z times 1 plus z0 squared over z squared. Now again, if we had a normal uniform beam here expanding, the radius of curvature would just go as z. You have some focus point, and as you move away, the radius of curvature, the center of curvature stays at that focus point, and as you move away, the radius of curvature just goes how far away you move. But that's not the case here for the Gaussian beam. If we go right at the beam waist, the radius of curvature is infinite, plane wave there. And if we go away a distance z0, now the radius of curvature would be z times 1 plus 1, or 2z0. So here we go a distance z0 away, and the radius of curvature is 2z0. Or if we go in the opposite direction, the radius of curvature then would be minus 2z0. But it changes only when you get far away does the radius of curvature go as z. And up close, it's kind of strange. So up close, as the beam propagates along, the center of curvature here actually moves. It shifts as you move along here, unlike a normal beam where the center of curvature would be fixed. Okay, and I guess that dashed line here is just the radius of curvature for a normal spherical wave. Well, then it behaves like a Gaussian. If you put that Gaussian profile on it, then it behaves. Then it is a Gaussian. Okay. that's something else that's kind of interesting. Again, as we get far away, it behaves like a normal spherical wave, but up close to the beam waist, it's a little bit different. So kind of a summary here of these strange behaviors, or behaviors, maybe I shouldn't say strange, is that at the plane, z is equal to z naught, so we're a distance z naught away from this minimum beam size, which we call the beam waist. The wave has the following properties. The beam radius is square root of 2 times greater than the radius at the beam waist, and the area is larger by a factor of 2. The intensity, or in your words, the irradiance, on the beam axis is half the peak irradiance. The phase on the beam axis is retarded by pi over 4 relative to the phase of a plane wave. And the radius of curvature of the wavefront is the smallest, so the wavefront has the greatest curvature, 2z naught. Okay. So anyway, those are some of the special properties of a Gaussian beam at these special points. Anyway, we could talk for a week on Gaussian beams, or maybe longer than that even. But I think that's essentially everything that I wanted to say. There's a little more in the handout I gave you, and but I don't think I'm going to go through that in class. Again, there are a lot of references on Gaussian beams that you can find, and I gave you the reference where I took this from, Fundamentals of Photonics by Soleil and Tisch. Any questions before we go on? Okay. Well, that finishes everything I was going to talk about for Chapter 16 then. So it takes us to Chapter 17. And I love Chapter 17. It's one of my favorite topics here. 17 is on holography. How many of you have made a hologram? Okay, quite a few. Good. Well, maybe you've heard me tell this story before, but I'll tell it again anyway, because it must be at least one of you who haven't heard it. Back when I was an undergraduate student in physics, I was planning to go to graduate school in solid-state physics. And one day in senior physics lab, this instructor brought in this cloudy piece of glass. And this was back when lasers were just were very new. We had a laser in the lab. So he took this cloudy piece of glass and he illuminated it with this laser beam. And we looked through it just like it's a window. And what I saw was a stapler. You know, and I was trying to reach behind the cloudy piece of glass to grab that stapler. But I could see it, but I couldn't grab the thing. And I mean, it looked so real. It looked, it was three-dimensional. It was red from the laser beam, but I mean, it's just like illuminating a stapler with a helium neon laser. And I don't know, somehow that just did something to me. I thought that was so fantastic. I couldn't believe it. So I said, the heck with this solid-state physics stuff, you know. I'm going to study holography. So I went to the University of Rochester, since this place wasn't quite started up yet, and studied holography. And it was a great time in holography. That it was the greatest thing ever. People were predicting how it was going to do everything. You know, 3D movies and 3D television, and you know, it was a time that was. It was so great that if you just mentioned the word hologram, people threw money at you. It was really very nice because everyone thought there was a huge amount of money to be made. 3 years later, when I got out of graduate school, though, by then they realized that holography wasn't doing everything that they thought it was going to do. And so then, if you mentioned the word holography, they ran away from you. They didn't want anything to do with you. So I just renamed it interferometry, and it worked fine. But holography to this day, it's absolutely fascinating. And some of the applications, I mean, they have become very large. Like, well, I mean, everyone here has probably almost everyone has a credit card, and on your credit card you have a hologram. So everyone in the world has everyone in the U.S. anyway has a few holograms, it seems. Money for counterfeiting, some countries put holograms on the money, so it's hard to counterfeit, or what I always say, it gives our graduate students some jobs with the mafia if you want to. But so areas like that where people didn't dream about in the 60s, holography has become very popular. Holographic elements, one example. Holographic non-destructive testing, which we'll talk about a little bit here, is another example of application. So there are a lot of applications for holography, but it took many more years for these to really happen than what people thought it would happen. And it's just a very, very fascinating thing. So let's talk about it here. First, go through a little bit of a physical description, and then we'll go through a little bit of math to show how it works, and then we're going to look at some applications here. And so 17.1, physical description. Well, I mean, it's almost magic. You take one beam, call it beam A, and you take another beam, and call it beam B, and you combine these two beams, and assuming the two beams are coherent, we're going to get interference fringes. And now we take some recording material, let's say film right now, maybe other materials that we'll use, but say film. We record this, and now if we take this and process the film, and if we illuminate this film now, so process film, we illuminate this with beam A. Lo and behold, what we get out of here is beam B. We'll get some other beams too, but if we're clever, and we'll soon learn how to be clever here, these other beams will separate in space. And so if I'm over here, as long as I stay to the right-hand side, this beam is exactly like what this beam would have been here, and it replicates it exactly. And that's independent of whether these are nice, clean spherical waves or if they're some complex whatever. You know, you can illuminate anything and get some complex beam, and this hologram is going to reproduce it. So some way it has stored all this phase information, phase and amplitude information in this recording here. So it's a very, I mean, it's very clever. This holography was invented by a man by the name of Dennis Gabor. In about, I think, 1947 or so. And again, I always like to think how he came up with this idea. He was, Dennis Gabor was a tennis player, and one day, waiting to get on a tennis court, he came up with this idea of holography. And later in the early 70s, he received a Nobel Prize for it. So I don't know how many of you are tennis players, but if you are tennis players, next time you're waiting for a tennis court, you know, just think. And you know, I've tried this for years, and it hasn't worked for me, but just think, and maybe you'll come up with something as great as a hologram. Okay? Well, anyway, Dennis Gabor, he made some holograms. If you go back and look in Born and Wolf, I think they show some pictures of his holograms and some reconstructions. But he had a lot of trouble back in the late 40s, early 50s. And his problem was he didn't have a good light source. And he used mercury sources, and of course you have to have coherence, so you to get the spatial coherence, you some way make the source look small, which means you probably focus it down on a pinhole, so you don't have much light left. To get temporal coherence, well, you have to put in some spectral filters to cut down the spectral width. So again, you don't have much light left. So he ended up with a case where he just didn't have much light, and he couldn't have much of an angle between the two interfering beams, because with the angle he got a larger path difference as he moved across the hologram, and he lost coherence. But if we come along into the early 60s, one of my favorite people in optics, Emmett Leith, and Upotniks in the EE department at the University of Michigan, got interested in the idea of holography from some work they did in side-looking radar. And that's about the same time that the laser came along. And Van der Loot had suggested to them to use a laser as a light source for holograms. And so they began making holograms, and I wasn't quite into optics yet. I was a little young yet, but at that point, that's when the world became really crazy, and they were so impressed with the holograms. And then finally, about 1965, when I got into holography, it really was sort of at its peak then. Well, anyway, let's go through a little algebra here to see how this works. And it's not too complicated, and it turns out it's just like, well, it's interferometry. That's all. Holography is interferometry. No, just a fancier word, maybe. So we'll go through a little mathematical proof of the reconstruction process here. So let's say that we make a hologram with some exposing intensity, irradiance, which is going to be, well, we're going to have two beams we're going to interfere. One of these we're going to call reference beam, so I'll call that U sub r. And the other one is the object beam, so I'll call that U sub 0, U sub O. And so that's the amplitude falling on our recording material, and we'll square that to get the intensity. And so and we've done this the whole semester here. But instead of writing it in terms of a cosine here, I'm just going to, when I square this, I'm going to write that as U sub r squared plus U naught squared plus U sub r U naught complex conjugate plus U sub r complex conjugate U naught. Okay? And so same thing we've been writing all semester, except in the semester we would write this as 2 times the square root U sub r magnitude U naught magnitude times the cosine of the phase difference. Okay. So now let U sub r, I mean some complex quantity, U sub r magnitude e to the I phi sub r, and U naught here is U naught magnitude e to the I phi naught. And so I here, U sub r squared plus U naught squared plus U sub r U naught e to the I phi sub r minus phi naught plus U sub r U naught magnitude e to the I phi naught minus phi sub r. So complex conjugate here. And again, as I said, the way we've been writing this all semester when we called it interferometry was we called that U sub r squared plus U naught squared plus 2 u sub r u naught cosine phi sub r minus phi naught. Okay. Okay. Now, generally here, what we could write we could say that u sub r, generally the magnitude of u sub r is not a function of position. And it's not going to be a big thing if it is, but let's say, so we're just saying it's a uniform beam, uniform intensity. And generally u naught is a function of position. So the object beam generally is, the intensity of the object beam generally is a function of position here. Now, this gets a little bit messy in a sense that we're recording this intensity or radiance on some material, film, let's say. And this recording material has some recording characteristics. And I want to go through here. I want to worry about that a little bit. It's going to turn out it's not going to be very important, but let's worry about it for the time being. Gabor actually worried about this a lot and went through steps to make the recording process, or the film processing process just right. So normally what the classical way of thinking about this anyway, and then we'll look at the more modern way, but the classical way of thinking about this is that for film, or recording material, if we make a plot of the density here versus the exposure, we get some curve that looks like this. And I said versus the exposure. Normally you make it versus the log of the exposure. And the exposure here E is the intensity times the time. And this is the density here. And that's defined as log of 1 over the intensity transmittance. So tau here is the intensity transmittance. Okay. And then I guess the other thing that we normally do when we do this curve is that there's a region here that's nearly a straight line. And so if we let this angle here be alpha, the tangent of alpha is what we'll call gamma. And the last thing I should write here is that this is often called an H&D curve. Okay, so this gives a relationship here between the density of the film, the log of 1 over the transmittance, the density of the film as a function of the log of the exposure time, of the exposure, intensity times time. And there's a straight line portion here with a slope of alpha, where tangent of alpha is equal to gamma. Okay, so now we're exposing this film. And if we stick just along the straight line portion, just along the straight line portion of this curve here. So along straight line portion of curve. The density is gamma log E exposure over some value E naught. So if I were to bring this back here, this would be log of E naught. Okay? And so that's log. Density is defined as log of 1 over the intensity transmittance, or if you like, that's just minus log of the intensity transmittance. So we could solve here then that the intensity transmittance is equal to E over E naught to minus gamma. Or I just write that as T prime E to the minus gamma. Okay. So anyway, this gives us then a relationship along the straight line portion of the H&D curve, gives us a relationship to the intensity transmittance as a function of the exposure, so as a function of the illuminating irradiance. Well, this is intensity transmittance, and we're working with coherent light, and in coherent light what matters is amplitude transmittance, and so I will call that right now in a capital T sub A. So that's the amplitude transmittance. Now, amplitude transmittance has associated with it a phase factor, and I'm going to neglect, for the time being, the phase factor. Let's assume that we don't have a phase factor here. And in practice, you can get rid of most of the phase factor if you take your film and put some index matching oil on it and put it against a flat surface. So you index out the height variations on the film. You still have a little, maybe, depending on the processing, a little phase variations in the film. But again, we're going to neglect that right now. And so this would be equal to, neglecting the phase factor, this is going to be equal to the square root of the intensity transmittance. Okay. And therefore, we could write, therefore, along the straight line portion of the H and D curve, we could write here that T sub A, amplitude transmittance, goes as some T double prime, E to minus gamma over 2. So we just took the square root of this. Now you might say, how can I, I have this H and D curve, how can I just worry about along the straight line portion of this curve? And what you can do is that you could, say, pre-fog your film to get you up to, so you could have some initial exposure independent of the hologram exposure that gets you up to the straight line portion of the curve. And then your hologram exposure is only along the straight line portion of the curve. And the amplitude transmittance then would go as some number times E to the minus gamma over 2. Okay. Well, let's process our film just right. So gamma is equal to minus 2. Process film. So gamma is equal to minus 2. Okay. And so now T sub A is T double prime E. Okay. And E here was just the intensity times the exposure. And so now if we take this and illuminate with the original reference beam, so now we'd have, say, U sub R, T sub A. So that's T double prime some number, U sub R times I, exposing intensity, times the time. And so when we multiply this out, come back here to the I, use this expression right here, we see that we're going to get a term here we're going to get a term. What's that? Back to here or back to the other one? This one. Okay. So here we're saying that we're going to illuminate the recorded hologram with the original reference beam. And so we're going to get something out that is proportional to the reference beam times the exposing intensity. And the exposing intensity went as, if I can cover this up, I'll take a sip of coffee, that's good. T is just a constant. It was the square root of T single prime. So now if we go back here, we're going to get light that comes out here that goes as U sub R times this mess right here. But the important thing is that when we do that, we're going to get a term that comes out as U sub R squared U naught, we're going to multiply U sub R times this term right here. So we're going to get a term that goes out as U sub R squared U naught e to the I phi naught minus phi sub R times e to the I phi sub R. So we're going to get a term that comes out here that goes as U sub R squared U naught e to the I phi naught. And so this is proportional to the original object beam. Okay? So independent of what the original reference beam was, or independent of what the original object beam was, one of these terms we're going to get out here goes as the original object beam. Okay? Reproducing it exactly. And this is just some factor multiplied times. Okay? That's one term we get. We're going to get another term here that is kind of interesting at times. And that's going to be this term here. So that's going to be U sub R times U sub R U naught e to the I phi sub R minus phi naught. And so that will be a term that's going to go as U sub R squared U naught e to the I 2 phi sub R minus phi naught. So this is conjugate to original object beam. Okay? So that's kind of interesting too. Well, we'll come back, but not today, but on Thursday maybe we'll get to look at this in more detail. That is kind of a strange creature. But in any case, if we could some way get this gamma equal to minus 2, then we would get back the original object beam. Okay, so that's kind of neat. Reproduces it regardless how complex it is. So then your question might be, what if gamma is not equal to minus 2? Is that what everyone was thinking? Okay. Well, we'll talk about that. What if gamma is not equal to -2? Now, when we make gamma equal to -2, that actually is a positive process, and so when we make a hologram, instead of having a negative, we're going to somewhat process it so we got a positive. And I guess Gabor's approach was to go through 2 steps. He got a negative, and then he made a copy of that negative, which became a positive, and he controlled the photographic process to get something close to -2. So what if gamma is not equal to -2? And this actually was my dissertation. And I tell you, if gamma is not equal to -2, as we'll soon see, doesn't make much difference. But I was able to get through my dissertation before they realized that, so it worked out okay. So what if gamma is not equal to -2? Well, let the exposure be some number here, but E sub c is something sort of like a constant. And so that is something like u sub r squared plus u naught squared times time. And that may not be really a constant because u naught may vary as a function of position. But it's some number here that, especially if the reference beam is very strong compared to the object beam, is almost a constant. And then we have an E sub v, which is this is the term that we want. This is the interference of reference and the object. Okay? So if we go back here to a e to the minus gamma over 2, and we say, well, gamma is not equal to -2, I don't know what it is, it's something else. So I could write that as an E sub c plus an E sub v to minus gamma over 2. And I could rewrite that as an E sub c to the minus gamma over 2 times 1 plus E sub v over E sub c to minus gamma over 2. So knowing me, what's the next thing we want to do? What do I love to do? I love to expand things, binomial expansion. Okay? So that's E sub c, the minus gamma over 2, times 1 minus gamma over 2, E sub v over E sub c, plus, this other thing, well, I'll write it down, gamma over 2 plus 1, 2 factorial, E sub v over E sub c squared plus so on. So if E sub v over E sub c small, then, we can neglect these higher order terms, and then the result is the same as for the linear case. Okay? So how do we make this small? Well, we make E sub c large. If we make the reference beam much stronger, much brighter than the object beam, then this quantity is going to be small. Therefore, make reference beam much brighter than object beam. And when I say much, 5 times, some number like that. Okay? And if that's the case, then what we get here is essentially the same thing as what we had when gamma was -2. We don't have to worry about the photographic process at all, and things work very well. And now if we think about what we're really doing here, is that the fringes that we're recording are sinusoidal fringes. And if we record these with a nonlinear process, the sinusoids will become, well, maybe not square waves, but more like square waves. Okay. And so if we have square waves instead of sinusoid, what do? We get more diffracted orders, therefore get more diffracted orders. Okay. But as we'll learn in our next class, if we make a hologram right, these diffracted orders will go in different locations, and they won't bother us any. And in fact, we already learned when we talked about gratings that the amount of light we get in the first order is actually a little bit better if we have square waves as opposed to sinusoids. So this nonlinearity, not only does it not hurt you very much, you can actually make it help you. Okay. So it works pretty well. Now I said, the classical way of looking at film is this density d log E curve. But if we're talking about holograms, it's not the density we care about, it's the amplitude transmittance. And so the curve that we really want to plot here is the amplitude transmittance as a function of exposure, TE curve. Okay, and that's not going to be as nice linear as I've drawn here, but anyway, that's a better way of characterizing the material than the classical d log E curve. Okay. So anyway, the effect is, Gabor worried a lot about the photographic process, and probably more than what he really needed to do. And so basically all you do is when you make your hologram, you make sure that the reference beam is a few times brighter than the object beam, and then the linearity or non-linearity of the photographic process does not bother you. Well, next class we want to come back here and look at the angles that we should have between interfering beams and how that affects the reconstructed orders and how you can separate all the different orders. And we'll go through a little algebra for that, and we'll talk about a little bit about recording materials and light sources, and then we will also talk about, as time goes along, maybe not next class, but we'll be talking about applications of holography. So I will see you bright and early on Thursday morning. Thank you.